Hi, I'm Clayton Myers. I'm a plasma physicist at Princeton Plasma Physics Laboratory, which is a national laboratory operated by Princeton University and funded by the U.S. Department of Energy. I study fusion energy research, or nuclear fusion, which is not currently used as a commercial or viable as a commercial energy source, but we're developing that technology so that in maybe 20, 30, 40 years, that fusion technology will be a mainstay in the world energy. So in undergraduate, I studied engineering physics and was looking for a research area that was exciting to me. And so I tried a few things and ended up in plasma physics, which has its main application in fusion energy. And so I started energy fusion research in undergraduate, and I did about 1.5 years of that and went to grad school looking for a fusion program and found the sort of the US seat of fusion here in Princeton. So fusion is a technology that requires decades of development, and therefore is something that's not funded privately at this time because it has such a long horizon. And so it is Department of Energy and federally funded facilities that are doing fusion research. And so in the United States, that means places like Princeton, MIT, General Atomics, and San Diego are doing federally funded fusion research. And so these graduate programs crop up in these large facilities. And Princeton Plasma Physics Laboratory is the flagship national laboratory for fusion research of the Department of Energy. There are about 400 or 500 employees at the laboratory, and 150 of those are physicists. And so we all work on a variety of experiments, mostly targeted at fusion research. Nuclear fusion is the exact opposite of nuclear fission. So in fission, you have uranium atoms that are very heavy, and you're splitting those atoms and getting energy out. Fusion is the exact opposite, where you're taking two very light atoms, sticking them together, and getting energy out. And it seems somewhat counterintuitive that you can stick atoms together and get energy out, but the difference is that the mass of the final atom is slightly less than the mass of the two atoms you put in, and that slight difference by Einstein's E = mc² equation is converted to energy. So up through iron on the periodic table, when you fuse, you get energy out. Past iron, when you split or fist the material, you get energy out. So we're fusing light atoms together to get energy out of that process. So plasma physics is my nominal field of expertise, not fusion. Fusion is an application of plasma physics. And the reason we need plasmas, which are a very, very hot gas, so it's the gas that's so hot that the electrons and ions in the individual atoms actually dissociate from each other. And so you have ions and electrons sort of flowing around in a soup. And the reason plasmas and fusion are related is because when you try to stick two nuclei together, there's a repulsion force. They're both positive charges, so the Coulomb force wants them to keep them apart. And so in order to get them to actually stick together and fuse, you have to have them coming in at such a high speed that they actually overcome that Coulomb force. And to have high speeds, you need it to be hot. So therefore we use a plasma. And in the approach that we study here in Princeton, which is called magnetic confinement fusion, we use effectively a magnetic bottle to contain this hot plasma and try to get many, many fusion reactions inside a device. There's also inertial fusion, where a small capsule is imploded and the inertial energy of everything crashing towards the middle causes fusion at the center. So there are several approaches to getting fusion reactions, but they all involve plasmas in one way, shape, or form because of the temperatures required. The past 10 years, fusion has had sort of a plateau, actually. So in the 90s, we achieved record fusion power outputs, both here in Princeton and at a Coulomb laboratory in the United Kingdom. And the last decade has been about developing real-time technologies and diagnostics to feed back into these machines. So these tokamaks, which is the name for the device that we do magnetic fusion in, it stands for toroidal magnetic chamber. That's the containment vessel, looks like a donut. And so the particles are magnetically confined and they just fly around the donut. So a tokamak is a toroidal or donut-shaped device that we use to magnetically confine plasma. And it has these circular magnetic field coils wrapped around the donut, and they produce a magnetic field that runs the long way around the donut. And the reason you want a magnetic field is when you have a plasma and you have a bunch of small, say, ions or electrons in your plasma, they can zip whatever way they want, completely random motion. And that's not very good for fusion because you want your particles to be confined for a long period of time. So if you happen to have a magnetic field in your plasma, these particles are confined like a bead on a string on those field lines. And so rather than being able to run randomly throughout space, they're forced to go along the field lines without contacting any physical vessel. So if something's extraordinarily hot, you want to have a no-contact confinement scheme. So if you happen to bend those field lines into a donut, which is what we do in a tokamak, the particles are forced to follow these field lines around the machine, and they just continuously whiz around and around and around as many times as they want, and hopefully stay confined and produce continuous fusion power. And there are many challenges to getting this confinement scheme to hold up, but that's the basic idea of a tokamak. The main challenge is that if we could make a fusion device that was a straight tube, we would already have fusion reactors. But if you do the calculation on how long does your tube have to be, it needs to be about the distance around the globe in order to actually have a straight cylinder. So when you bend it into a circle, you introduce non-uniformities in your magnetic field. The magnetic field is actually stronger on the inside than it is on the outside. And so that causes particles to want to leave radially outward. So we have all kinds of ways for compensating for these radial drifts that are kicking particles out. And the plasma is turbulent, so if it wasn't turbulent, it'd be wonderful, but it is turbulent. And so particles can travel through turbulent eddies out. And so the entire game of operating a tokamak is to try to minimize all of these effects that degrade confinement. We want the maximum confinement possible because that gives you the maximum fusion power. Come such a long way. When we started back in the 50s, I say we, my predecessors started back in the 50s and 60s, confinement was terrible, meaning that the amount of fusion power we were getting out of the device versus how much we had to put in was 10 to the minus 6, so many orders of magnitude below 1. We ultimately want to get to the point where we're obviously producing more power than we put in. And we've come almost all the way to the point of 1. We're actually at about a half right now. And so we're very, very close. But there are two actually major issues still standing in our way. The first is what we call disruptions. And this is where your tokamak is moving along just fine. And I talked about instabilities at the beginning. There's an instability that crops up and all the energy stored in your plasma crashes with a bang. And this is something we haven't been able to avoid in tokamaks. And this is actually what I'm going to be studying over the next few years, is tokamak disruption. The second is wall materials. You have this plasma, which you can construe as the world's largest blowtorch, nearby to a wall that has to be made of something. And there are enormous issues with what material are you using as the material that's facing the plasma. We call it a plasma-facing component. So there's an enormous material science effort underway looking at possible wall materials. And on the plasma physics side, we're looking at ways to keep the plasma away from the wall and give it some buffer to make it less damaging to the materials that are nearby. So both disruption issues, meaning that you don't want your power plant to turn off in the middle of operation, and first wall issues, meaning that if you want this to be a power plant for 30 years, you have to have materials that will survive those extreme conditions of the plasma for that amount of time. So the materials that we use on first walls right now are actually from the space program. So we use, effectively, the wall materials we're using at the moment are space shuttle tiles. So what was developed for the heat shields in the early space program and then extended to the space shuttle program is what we use on our walls, which is carbon-carbon or something like that. Unfortunately, carbon-carbon is not a great material for a reactor in the end. It's good for experiments, not great for a reactor. So we're developing new materials that may eventually have some transfer, but right now it's in such an early stage that I would say no, those materials aren't being used elsewhere. So we have several of these devices here in Princeton, one very large one, a few smaller ones. And this has been a concept that's been around since the mid-60s, let's say. And it was originally invented by the Soviets and was brought here to Princeton also in the 60s and has been studied since. We've gotten better and better at controlling the plasma in these donut configurations. And so the last 10 years has really been, I would say, about plasma control and learning to use real-time systems so that if the plasma is healthy, we just let it go. But if it starts to become unhealthy, we can actually detect these sort of sicknesses in the plasma, and we have magnets that push back and try to keep the bulges inside the donut from growing so that the plasma continues to fuse. And so these are our biggest advances in the past 10 years. And part of that has led to new machines that are being built. So we have a very exciting few decades on the way in the fusion program. An ideal plasma would be completely quiescent, and these particles would whiz around, and it would be very, very quiet. So when we sense, say, fluctuations in the magnetic field, we would minimize those. But the plasma, since we're trying to hold all this thermal energy in a bottle, the plasma is very clever, and it wants to find ways to get out. And so instabilities are a way of taking that thermal energy and destroying our ability to bottle it up. And so when we say we have a sick plasma, there are many, many instabilities that crop up that can destroy the plasma configuration. And our goal is to try to suppress those instabilities and kind of hold the thing together so that we can get energy out. Energy is something that is universal throughout the world. Everyone desires energy, everyone uses energy, and we're all, I think, well aware of the climate issues and also the growing energy demand with developing countries like China and many other places. And so knowing that energy is going to continue to be an enormous problem, and actually it's going to be a growing problem over the coming decades, drives me to be in a field that is working towards what we consider to be clean energy. And fusion is very clean compared to fossil fuels, compared to fission, actually. And it's very safe. And so, though it is difficult, it is worth the effort because of the payoff in terms of meeting the global energy demand as we continue through the next few decades. I am. I think that human civilization exists because of our ability to survive, and part of that survival is happiness. I think that when people are happy, we have a better chance of survival, and since we're survivalists, that people are going to continue to be happy. There's going to be good things and bad things, but happiness is a part of our survival, and so I am optimistic that we will have a happy, prolonged civilization, and that we will make good decisions in that regard. The final goal of my research, or fusion research, if we're focusing on that, is to produce world-scale energy, meaning an energy source that is long-lived, relatively safe, and can provide a very large percentage of the world's power. So there is an economy of scale with fusion. So you're not going to, it's unlikely, I won't say you won't, but it's unlikely that you're going to produce a bunch of very small power plants. It's going to look something like the structure today, where you have large coal plants, large fission plants. You're going to have large fusion plants that are producing, say, 3 gigawatts of thermal power and converting that into about 1 gigawatt of electricity that gets distributed over a grid. So really it's just changing the heat source in your power plant. All the stuff outside of the heat source, the steam converters, the turbines, the generators, the distribution network, is all the same as what we have now. It's not looking to replace that network. It's just changing what is providing the heat at the center, and that would be fusion reactions instead of coal or fission. There are actually an amazing number of technologies. We refer to it as technology transfer that happens from my laboratory, from many other laboratories. And the one example that's a good one is basically in nuclear detection. So as part of the fusion program over the past 50 years, we had to become experts at detecting neutrons, because when you want to say how much fusion power do we have coming out of our device, that you're measuring the neutrons that are coming out. And so we got very good at detecting neutrons. Well, that's also useful for detecting, say, nuclear warheads or other radioactive waste or something being moved. And so when you have a port in your country that is wanting to scan and say, do I have nuclear weapons, not certified nuclear weapons moving through my ports, and detect those things. So we actually have created several systems at our lab for nuclear detection, and also for warhead verification is something we're doing recently, where you don't actually have to know exactly the details of the warhead, but you can verify that it is in fact the warhead you want. It's called zero knowledge protocol, and this is something that just happened in the past month actually at our laboratory. They've started an experimental program for that. So there are all these spin-off technologies related to our nuclear science experience that are impacting other areas. So the joke is that it's been 25 years away for the past 50 years. And that's to some extent true, unfortunately, is that the amount of fusion power we're capable of producing has gone proportional to the amount of funding, because as I mentioned at the beginning, this is a government-funded, internationally government-funded research and development effort as opposed to a privatized effort. And so as politics change, all these things, the amount of funding coming in changes. And so, like I said, the 90s were a very big boom time for fusion because we had lots of funding and we were able to set all kinds of records. But the funding has gone flat. It hasn't gone away, but it's gone flat over the past decade. And so we've made incremental progress, but we're looking for game-changing steps. And the pace at which we achieve those game-changing steps is going to determine ultimately how long it takes. Now, to put a number on it, I think we're looking at 50 years. Again, I mentioned economies of scale. So your fusion power scales with your plasma volume, but the other thing that scales is that right now in our tokamaks, we only have the center of the donut, the very center line around, is hot enough to actually produce fusion. And all the rest of the plasma volume is the interface between the walls of your vessel, which are room temperature or close to it, and that 100 million degree center, 10 million degree center, very, very hot. And if we can improve the amount of the plasma that's filled with very, very hot gas and not have such a long transition, we can make the machine smaller. So we're doing some things in Princeton to try to make more of the plasma volume actually produce fusion power, and then you don't need such a big device. But just when you do out the scales of how much plasma do you need that's actually producing fusion power, you need a machine that big to get there, unfortunately. I think that there is almost an unrivaled chance with fusion power for global impact. There are two games in energy. One is electrical grid power and the other is transportation energy. Fusion is not a transportation energy. It can be if you run on an electric car economy, but first, to be clear, it's producing grid power first and foremost. But that's a huge game changer for climate change because fusion is capable of replacing fossil fuels, flat out. Whereas you can question whether solar and wind are capable of producing enough energy to take over the base load on your grid. Fusion is completely capable of doing that, and we hope will do that. So that's one. The second is the fuel. So the primary fuel that goes into fusion is deuterium, which is an isotope of hydrogen and is actually naturally present in seawater. So anyone who has access to seawater, which is almost everyone, can get their fusion fuel for almost free. And so that changes the economy enormously globally in terms of who's hoarding natural resources, who's rich in fossil fuels, who's not. Hopefully that changes that economy massively. I think there are a few technologies out there that have the potential to reset the global landscape compared to this one, which resets the entire energy economy. In the next 10 years, I think that I'm going to do this through the lens of energy as I have been doing everything else, but energy demand is going up almost exponentially in places like China and the developing world. And that's a scary thing from the standpoint of then you're exponentially increasing environmental impacts from building massive amounts of coal plants. And I think that that's going to be a big challenge, even in the next 10 years. I don't think this is something that's 50 years away, like fusion maybe. I think this is something that is very near term, and energy demands are going to continue to drive geopolitical factors, maybe even more so than they already have. There's two ways to go about this. One is to say that there are some frightening technologies on the horizon, whether it be, they're frightening and exciting, but things like artificial intelligence and things like that, genetic engineering and all the moral quandaries associated with that. The other way to look at it is, and this is a fear not so much of science and technology, but for science and technology, is that one of the most important things we can do as a society is to invest in science and technology. We are given, as a species, the incredible capacity to to innovate and use the world in which we live to make lives better for society. And so my fear is for science and technology that we don't maximize that potential for innovation from our species by underinvesting, whether it be on the federal level or the private level, or investing too much in menial technologies that don't, that make someone wealthy but don't maximize our potential for innovation. So I would say my fear is underinvestment, honestly, in the sciences. So I think the obvious quality is natural curiosity. You have to be curious about what you encounter in the world, and this extends far outside of the laboratory. It's in gaining knowledge about what's out there and wanting to understand and categorize what you see. And so that's something that is just a natural feature of a scientist, that you have to be curious and desire information. And science is all about studying a very specific area, but gaining information and gaining understanding. And so it's that natural desire to do that. Another thing about science that I think is undervalued is communication skills. And it's very important to obviously discover things, but if you cannot communicate what you've discovered, then it will not have the impact on society that it otherwise could have. And so, especially as we continue to become a globalized world and a globalized society where we're doing science across international boundaries, and projects like ITER that I mentioned, where you have half the world's population involved from a nation standpoint in this project, really communication is almost as important as the science itself. Again, through the lens of energy, because that's what I'm focusing on here, is everyone needs energy. Not just in the CERNs and the Princetons of the world do we need energy. And so I would advise that the local politics, the local infrastructure that you have in Bulgaria is a very important thing for your country. And to get involved in the energy future. And as fusion develops or fission is adopted, Bulgaria is going to be making those decisions just like every other country in terms of where do we take our energy portfolio, how do we invest in our infrastructure to deliver energy more efficiently, or as we move into the 21st century, more and more technologies require more energy. So every nation is going to have to be building better infrastructure for this. So getting involved in the local decision processes in Bulgaria and engineering and research and all those things, it's not something that happens only in a few places in the world. Energy is something that is needed everywhere and demanded everywhere. This is something we see in the United States for sure. It's what I'm more familiar with, but infrastructure investment has one of the highest returns per dollar in terms of back to the society in which makes that investment. So whether not just energy, but roads and bridges and all these things, I absolutely advise you to get involved in those careers, in the sense that you're maximizing your contribution to your society and making an impact both global and local by being involved in infrastructure things.